Okay, so I want to start by talking about the nature of inverse square laws. An inverse square law is any physics law that has the proportion one thing is inversely proportional to 1 over something else squared. Okay? Where y and x can mean anything, any physical quantity. So there's a lot of these in physics, a lot of these in science, even in chemistry, I believe. The one that we're going to focus on is law of universal gravitation, obviously, but there are other ones. The way that light behaves as it spreads out into three-dimensional space obeys an inverse square law. The way that sound dissipates as it travels out through three-dimensional space. Pretty much anytime you have something that spreads out into three-dimensional space, the way that it dissipates with distance is going to be an inverse square law. Okay. So the one that we're dealing with is the force of gravity. And it obeys an inverse square law. The proportionality constant is big G. And then you got two objects, M1 and M2. The force of gravity directly proportional to the product of those two. Inversely proportional to the distance between them squared. And the scenario would be, say, mass 1. Could be a planet, could be a star, could be one of you guys and someone else on the other side of the planet. Yes, there's a gravitational force between you and someone on the other side of the planet. There's a gravitational force between you and every single person on the planet. It's just real tiny. It's real tiny. And these objects are separated by a distance r. Okay. And then big G is 6.67 times 10 to the negative 11th. The units are weird. The units are newtons. Newtons times meters squared per kilogram squared. Why does it have those weird units? Well, if G has those units, this meter squared cancels with this meter squared. This kilogram squared cancels with the 2 kilograms for the masses, and I'm left with units of newtons whenever I calculate a force. Right. Okay. Now, I do want to specifically talk about, I don't go into this discussion with pre-AP, and definitely not on level, and that's because they use D instead of R. Okay. But the big kid version uses an R. And that's because we're dealing with vectors. We are technically dealing with vectors when we're talking the law of universal gravitation, which means I need some coordinate system in which to measure these vectors. And generally, if this is like a star and this is a planet, you just call the center of the star the origin of your coordinate system. And remember, if we have positions along the x-axis, then we can call positions x0 and x. If we have positions along the y-axis, we can call them y0 and y. But what if I have a position, let's say I have a coordinate system like this, but I have a position that's right there, that's not in the x or the y direction? Well, in that case, we have to use a more generalized symbol to indicate position, and that symbol generally is r. Okay, that's this r. But technically it's because we have to define a coordinate system, usually the center of the larger object, and then we measure the position with a position vector for the other object. And so that position vector would be this, right? That position vector has length, r. And so that's why we use r here. Technically, this is a vector equation. The force is a vector. So technically, we know the force on M2 is pointing this way. Force of gravity on M2 is pointing that way. So technically, there's a negative here, right? There has to be a negative here because if r is positive, then the force of gravity is negative in that same coordinate system. You don't need to use that because in this class, when it talks about gravitational forces, they're talking about the magnitudes of gravitational forces. And when you're talking magnitudes, you don't need to worry about direction. I feel like it's my responsibility to tell you why this is not D, though, and why it is R. Especially if you go on to higher levels of mathematics and physics in the future. Okay? All right. So, the nature of inverse square laws. Let me ask you this. Let's see. You want this to be second nature. This is M1. This is M2. The answer to this question, you want to be second nature by the end of this period, separated by a distance r. And you know that there's going to be a gravitational force on both of these objects. And we know that that gravitational force will be equal in magnitude. or these gravitational forces will be equal in magnitude and opposite in direction by Newton's third law of motion. What if I took M2, I grab that planet, and I just move it twice the distance? So I move it out to here. The same planet, I just grab it and I move it, I double its distance from its star. So now instead of r, I would have a distance 2r. What do you think is going to happen to the force if I double the distance? Is it going to quadruple?
It'll like to
Whoop.
like it'll get quadruple times as weak.
Yeah, it'll be 4 times weaker, right? Yes. Or it will be 1/4 as much, right? Now, a lot of students get stuck in the mindset, well, if it's double the distance, they know that it's going to get smaller, right? The farther away from an object you get, the weaker the gravitational pull on you will be. And so if I double the distance, it should go down. But what do a lot of students think? If you double the distance, you get 1/2 of the weight, or the gravitational force. Same thing. But because the law of universal gravitation is an inverse square law, it's inversely proportional to the square of the distance, it's going to be 1/4. Because you're going to take this 2r and you're going to square it. Okay. What if I triple the distance? It's going to be 1/9 the force. What if I increase the distance by a factor of 10? That's if it's 4. Increased by a factor of 10. 10 times farther away. 1/100th of the force. What if I got twice as close? What if I cut the distance in half? It'd be 4 times stronger. Yes. Okay. Now, if that's not obvious, you got to do it the long way. And whenever the problems get more complicated, the specific type of problem I'm talking about, you got to do it the long way. Okay. So doing it the long way, I would say, okay, my original gravitational force, I know is given by Newton's law of universal gravitation, which is this. Now, a lot of textbooks and a lot of notes that you'll see, a lot of example problems will use this notation. They'll say, okay, I'm going to change things. In this case, I'm going to double the distance from the star to the planet. And a lot of notes, a lot of textbooks will say, the new force I'm going to call Fg prime. Those of you in calculus, this is not the derivative. This is not the derivative. That's why if you're in calculus, you might want to call this Fg1 and this Fg2. It just means new force. Okay. And this is the type of problem, by the way, I'm talking about. I have a situation, but then I'm going to modify that situation, and I want to see how that modification affects my results. Okay. Not just for this kind of problem. This kind of problem can be applied to any physics concept that you can describe with an equation. And the general steps that you take when you see this kind of a problem, you get an equation for the first scenario. Then you modify that equation with the second scenario, work through the math, come up with your result, which we're going to do now. So my new gravitational force, when I make that, so here's my original scenario. I modify this scenario. Notice I don't have specific numbers here. I don't have the masses. I don't have the distances. I just want to say, in general, if I double the distance, what happens? Right. So the modification is that I take r and replace it with 2r. Okay, that's the modification that I'm going to make in my new equation. Same equation, Newton's law of universal gravitation, but I got to make that adjustment. So it's going to be big G times m1 times m2 over not r squared, but 2r squared. And because r itself gets squared, when I double r to get 2r, that whole quantity must be squared. And your properties of exponents should be pretty ingrained in your brain by now, especially if you're in pre-cal. What is 2r squared?
4r squared.
Yeah, that 2, that squared applies to both factors, right? So that's going to be 4 times r squared. And I like doing it this way. I like saying, all right, I want to rewrite this with the original expression and then bring the numbers out into the front. So if I bring the numbers out into the front, any numbers that weren't there originally, I'm going to bring out a 1/4, right? That's the 4 in the denominator. I pulled it out. 1/4 times g m1 m2 over r squared. Notice that g m1 m2 over r squared is literally my original equation. Therefore, I can replace it with just the original gravitational force, F sub g. And so, in conclusion, my new gravitational force is going to be 1/4 of, remember, of, the word translates into multiply in math language. So my new gravitational force is going to be 1/4 of my original gravitational force. Now, if it's easy like this, though, if it's just doubling the distance, then you can do that in your head. And you can say, well, inversely proportional to the square, so I got to square the 2, and I get a 4 in the denominator. So it's 1/4. If it's 5 times farther away, I put a 5 in the denominator, and it gets squared, so it's 1/25, right? Just so you know, if instead we cut the distance in half, the reason we end up with 4 times as much is because I replaced r with 1/2 r. So when I have 1/2 r in the denominator and it gets squared, I have big G m1 m2 over 1/4 r squared. Well, that's a compound fraction. I'm going to rewrite that because that makes me uncomfortable writing it like that. So I'm going to say G m1 m2. Make the numerator a fraction by just putting it over 1, the ninja one, the invisible one, over r squared over 4. Right, 1/4 r squared is just r squared over 4. And then you flip the guy, multiply, right, when you divide by a fraction. So you'd end up with a 4 in the numerator, 4 times G m1 m2, and r squared ends up in the denominator. So 1/2 the distance, I get twice as close. I end up with 4 times the force. So if I get to 1/3 of the distance, I'll have 9 times the force. If I get to 1/10 the distance, I'll have 100 times the force. That's the nature of inverse square laws. Okay? Does that make sense? You feel good about it? Sweet. Feel good? All right.
Super good.
Did you know that you would?
Yeah.
Okay. Let's look at a more complicated example of the same kind of problem. Let's say I have a star and I have a planet. I'm going to use slightly different notation here just to show you can use different notation, especially if you're in calculus and you don't like using the primes. I have a star and a planet that are separated by a distance r. And the problem might say, what would happen to the force, I'm just going to write F sub g, if the star was 4 times as massive and the planet was 1/2 as massive and 4 times further, whatever, from the star. This, some people can do in their heads, these types of problems, but it's a bit more complicated because now you're not just doubling what's in the denominator, or squaring what's in the denominator, right? Now we got a bunch of different things that are changing. Well, again, and this is a specific type of problem. Notice no specific numbers are given for the masses, for the gravitational forces, for the distances. They're just saying, here's the situation. Then you're going to modify it, and you're going to see how the results are affected. Okay. So let me actually show the forces real quick. Okay. And I'm going to use a little different notation here. I'm going to say, those should be the same size. I'm going to say FG1. we're going to call this force of gravity 1. And then the new force, I'll call force of gravity 2 after I've made the modifications. And again, in this type of a problem, the first thing you need to do is, well, we already did.
Well, but for the new one.
Okay. So, well, no, the free body diagram for the new situation will look the same, right? It's just going to change. The size of the force will change. I'm talking about this specific, you just get farther away, but you don't technically need to draw it again.
Okay.
Because it'll literally look identical. They'll be farther away and the forces will have gotten smaller. That's it. Well, you don't know. You don't know because the star's getting bigger, right? And so you got to actually show, well, did it get smaller or did it get bigger? But the thing is that when you have a question like this that doesn't give you numbers and says if you modify the situation, what's the result? Or what can you say about the result? You need an equation for the thing it's talking about. Okay, so I need to get an equation. We already have one, but sometimes you don't. As you'll see in units down the road, you'll have to get equations by doing some physics and then do a problem like this using that equation that you have to derive. So I already have the equation. The equation is the force of gravity, and I'm going to say comma 1, the first force of gravity that describes this situation is going to be big G. Instead of M1 and M2, I'm going to put MS and MP for mass of the star and the mass of the planet. It means literally the same thing. Divided by the distance separating them squared. Understand that R does not need to be, it's not a radius. It doesn't mean radius. It literally means position vector. Sometimes it is a radius. If this planet was in a perfectly circular orbit, it would be the radius of the orbit, right? But understand that sometimes it is a radius, but it's technically not. Technically, it's just a position vector that has the length that, again, sometimes is a radius. All right, so there's my first one. Now I have the equation. Now I need to replace the things that get modified, right? So instead of mass star, I'm going to replace it. Well, the star is now 4 times as massive. So I replace that with 4 times mass star. Mass of the planet, I replace with 1/2 mass of the planet. If you're like me, you like writing MP over 2 instead. That means the same thing. Hopefully we all know that. And then the distance is 4 times farther. So R gets replaced with 4R. So I'm going to throw all those new things in and then manipulate the equation so that at the end I see this and I have some numbers in front of it. And the numbers in front of it will tell me how the original force was modified by how it changes in response to making these modifications. It's not you physically do this. You can't make the star bigger. And this is just saying that, well, if you were to do that, what would happen to the force? It builds intuition as to how the forces will work in different scenarios. Okay, so let me make those substitutions. So Fg2 now, my new gravitational force, will be big G times, instead of mass star, I write 4 mass star. Instead of mass planet, I say mass planet over 2. And instead of instead of distance r, I replace it with distance 4r, but then that gets squared. really recommend using parentheses for multiplication. Right, the little dot, the x we dropped a long time ago. The dot, you should probably start phasing out too. Yes, you can use it every once in a while, but parentheses is much neater and it helps you avoid mistakes. At least it helps me avoid mistakes. All right, so now I need to deal with the numbers here. And when you were small children, you learn the properties of addition and multiplication. The associative, the commutative property. The commutative property of multiplication says it doesn't matter the order that you multiply things in. So I can take this 4, I can move it out into the front. I can take this 1/2, move it out into the front. And then what do I have left over? Just G mass star mass planet.
Yeah, over 4.
And then here I'm over 4?
Sorry, 16.
16. I got to square that. So 16 times r squared.
Why wouldn't you just cross simplify on the...
You can. If you can simplify the math here, that's fine.
Okay.
But I'm doing it this long way. Yes, you can cancel this 4 with that. You can cancel that 2 with that 4, and you're left with the 2 in the numerator. That's fine.
Cool. Just
because we do the same thing here, right? 4 times 1/2 is 2. And so I can replace that with 2. G mass star mass planet divided by 16 r squared. My new gravitational force, and many of you probably know the answer already, but again, I'm doing it the long way. I'm going to bring the numbers out in front, write them out in front, 2 over 16, times what's left over, big G, mass star, mass planet, divided by r squared. And the reason I like writing it like that is because big G, mass star, mass planet over r squared is literally my original gravitational force. Okay? So now I can write my result as the new force of gravity, if I were to make these modifications in the system, would be 2/16 is 1/8. 1/8 of my original gravitational force. So if I had a star and a planet that had a gravitational attraction between each other, and I made that star 4 times more massive, and I cut the mass of the planet in half, and I moved them and separated them by a distance 4 times greater, the gravitational force between them would in fact be 1/8 of the original force. What was that?
No, I was just saying what you had said.
Oh.
Yeah.
That makes sense?
On the same page.
So this what I just did here is very similar to problem number 11. It's the last one on your quest assignment. Okay. And if there's no other, and if you need clarification, you got questions, please ask them now, because I am going to go on to another example problem that will be very much like number 9 on your quest assignment, and those will literally be the 2 most difficult problems on the quest assignment. So any clarification needed here? You good? All right. Solid. Am I? Yes, I'm recording. All right. So this one's going to be more like number 9. So let's say it's Gavin. So here's the Earth. So here's the mass of the Earth. And since I can't draw, here's Gavin.
That looks
Massive.
just like you, Gavin.
Massive Gavin. Okay. And remember that the gravitational force is literally the weight. Literally the weight force, right? Fg, we saw yesterday. You can get the same result. You can actually calculate G by using Newton's law of universal gravitation. Right? That's actually how we know that the force of gravity is literally mg. So I know that Gavin feels a gravitational force that points down. And we'll call this Fg. We'll call this Fg, Gavin's weight. And yes, there's a force that acts on Earth that points up, but that's not going to affect the motion of Earth at all, so I'm going to just kind of ignore it. We're just interested in Gavin right now. Okay. So let's say that Gavin is then, so he gets transported to a spaceship orbiting the Earth at 2 times the Earth radii above the Earth's surface. What is his new weight if he weighs... You know how many pounds you weigh? You don't have to say if you don't.